in the AI Infra Connect series. My name is Ruby. I'm the Portfolio Director for the AI Infra Summit, and I'm delighted to be joined today by Archana Cheruliyil, Principal Product Manager, Marketing Manager at AlphaWave Semi, for today's webinar on advancing AI, the role of HBM in the chiplet ecosystem era. Thank you so much, everyone, for joining us. Shortly, I'll hand over to Archana, who's going to deep dive into some insights on the role of high bandwidth memory for overcoming bandwidth and latency challenges in AI hardware, give an introduction into HBM4 innovations, and discuss a bit about how AlphaWave Semi is contributing to innovation across the memory landscape. Just before I hand over to Archana, just a few logistics for all of you watching. You will see some tools to interact on the right hand of your screen, including a Q&A box. Make sure that you ask all of your questions as they come in throughout the session, because we'll have time for a Q&A with Archana at the end. After today's session as well, if we don't have time to get to any questions, then the AlphaWave Semi team will reach out and follow up with you. So feel free, any questions that you have, to ask there. A recording of today's session will be available from tomorrow. We will send you this in a link. So don't worry if you miss anything, you can watch it on demand from tomorrow. And yeah, without further ado, I will now hand over to Archana. Looking forward to today's session. Welcome, Archana.
Thank you so much, Ruby. Good morning, everyone, and welcome to today's webinar, Advancing AI, the Role of HBM in the Chiplet Ecosystem Era. I'm Archana Cheruliyil, Principal Product Marketing Manager at AlphaWave Semi. Before we jump in, I just want to give a quick look at today's agenda. So first, we will start by looking at how AI workloads are growing exponentially, driving massive data and compute needs, and how specialized hardware is critical to handling AI scale and speed. Next, we'll look at some of the advanced memory, packaging, and interconnect technologies and how they're fueling AI system performance, including some trends that we are seeing in 2.5D and 3D packaging. Next, we look at how HBM is the cornerstone of technology that is essential to keep up with the demands of AI systems, and why custom HBM solutions are key to unlocking even more system performance. Finally, we'll end with some summary and key takeaways. So let's jump right in. So why is data consumption growing exponentially? Let's take a look at the chart on the right. So this chart is a measure of all of the data that is currently stored on our planet. You can see for the first half of the previous decade, data was growing linearly. During this period of time, data was being generated by humans via PCs and cellular phones. However, in and around 2017, sensors, images, and devices began being deployed, and data started to be generated by machines rather than humans. This trend of autonomous data generation accelerated the amount of data and transitioned us from linear growth to an exponential growth. This massive growth will result in the amount of data in the world doubling by 2025. This creates the next inflection point and opportunity for all of us, which is AI. Given this massive data growth, how has the industry responded to this massive growth in data? It is becoming apparent that the monolithic designs are approaching reticle limits, and transistor scaling has not quite kept up with the demands of compute. Single chip performance has maxed out, and we either need to add more silicon, either on package, or network more chips together to get more performance. This has led to a rise of custom silicon implementation and the emergence of chiplets for AI infrastructure. Chiplets can afford great flexibility and modularity to the overall system performance, and we will explore this a little more today. Another notable trend that you will see is the emergence of high-performance GPUs or XPUs, which has massive parallelism that has been the workhorse behind some of these AI systems. In the memory domain, HBM remains the AI memory of choice to feed the AI engine and its unparalleled bandwidth density performance. Now that we've kind of taken a look at the landscape and how AI is driving these massive amounts of data generation, Let's understand some of the most important technology trends that is driving next generation XPU designs. And one of them I want to talk about today is advanced packaging. 2.5D integration has enabled this aggregation of systems on package. This has fueled a wide adoption of UCIe standard as the die-to-die interface for chiplet-based architectures. We are now seeing UCIe march towards an impressive 64 gigabits per second data rate that will ease some of the performance bottlenecks we are currently seeing in the industry. 2.5D packaging has been enabled currently for high volume manufacturing on a 55 micron to a 45 micron bump pitch, and it is steadily scaling down, as you can see on the graph on the right. Foundries and OSATs plan to further scale this down to around 25 microns bump pitch, which will enable very high bump density and bandwidth efficiency. Now, we all understand that communication between chips happens on the shoreline or the perimeter of the chip, and there is just not enough shoreline available today to satisfy the bandwidth and latency demands of parallel compute engines. We are now entering the next generation of advanced packaging, which is 3D stacking. This will enable bump pitch as low as 9 micron and the roadmap going all the way down to 6 micron and 4 micron. With this information, let's take a deeper look at some of these technologies. So we understand that packaging technologies play a crucial role in integrating chiplets. On the left, you see a standard package mock-up. So traditional organic multi-layer package substrates are limited by bump pitch requirements, usually around 110 to 130 micron. While this is cost-effective, bandwidth per millimeter, which is basically how much data and information that you can pack on the shoreline, is limited because of the small number of routing layers that is available to a designer. Next, if you look at the advanced packaging section here, we have packaging technologies like silicon interposer and silicon bridges, which offer much finer bump pitch, less than 55 microns for much higher bandwidth density. Silicon interposers in particular are popular for integrating chiplets with HBM or high bandwidth memory. These are, however, limited by the size of the interposer and the number of metal layers that are required for deeper I/O connections. The next here, what I'm showing you is an RDL type of an interposer, which is a redistribution layer. This is another option for chiplet integration that has been developed as a more flexible alternative to a silicon interposer. The RDL interposer has extremely good signal integrity performance due to its use of very low loss dielectric materials and thick metal traces, which result in overall lower insertion loss. Sorry about that. So we are talking about the RDL interposer. Another major advantage of RDL interposer is that it is extremely good choice for external signals such as high-speed SerDes because your signal integrity is guaranteed. It can be used also to integrate multiple chiplets and memories without the limitation of form factor that is present with the silicon interposer. Additionally, RDLs do not have through-silicon vias or TSVs like the silicon interposer, which again makes it an excellent choice for routing longer distance communication IOs like SerDes and PCIe. However, given all of these advantages with RDL, it also has some limitations. One of its limitations is its lower integration density and potential routing feasibility issues due to the larger size of vias and pad size. To address these limitations, a new technology that combines RDL and silicon interposer called the silicon bridge has been introduced. This allows for directly connecting power and overcoming the challenges of limited vertical connections. Silicon bridges offer similar bump pitches with no reticle limit, making it possible to integrate large and multiple dies. The bump pitch of the silicon bridge is similar to that of a silicon interposer, and the area outside of the silicon bridge is the same pitch as that of a regular C4 bump. This area outside can be used for external interfaces such as Ethernet and PCIe, and that don't have to go through a lossy TSV channel. Now, if you look further on the right, my third mock-up here, These are some of the more recent advancements with 3D stacking, where you stack one die on top of another die. The top and bottom die could be from different process technology nodes, and communication happens through hybrid bond connections. The bump pitch currently available is for hybrid bonds is somewhere around 9 microns today and steadily driving downwards. There are currently two configurations that are supported with a 3D stacked configuration where you have a face-to-face and a face-to-back configuration. In the face-to-face configuration, both of the dies are facing towards each other. And in a face-to-back, your top die is face down on your bottom die. This type of connection provides very low power and highly reliable interconnects at very low latency, a win-win-win for AI specialized hardware. Ultimately, the choice of technology really depends on factors such as the required bandwidth, power consumption, form factor, and your overall system cost. Now that we've understood the driving force in terms of the advanced packaging technologies available to us, let's take a look at HBM technology that was really our first foray into chiplets and which does leverage the 2.5D technology. So high bandwidth memory has been around for about a decade, and throughout its continued development, it has steadily increased in speed, starting at a data rate of 1 gigatransfers per second, which was the original HBM, and reaching upwards of 9 gigatransfers per second for the latest HBM3E. This has made an impressive jump in bandwidth in less than a decade, making HBM an important cornerstone for a whole new class of HPC accelerators that have since hit the market. Compared to HBM2 and 2E, HBM3 delivers greater bandwidth, but it has also introduced significant advancements in terms of power efficiency, memory access, and RAS, which is reliability, availability, and serviceability. HBM3, for example, reduces the core voltage, dropping it to 1.1 volt compared to the 1.2 volt of HBM2E. Additionally, HBM3 has also lowered the I/O signaling voltage to 400 millivolts. These voltage reductions translate into better power efficiency, which also help offset some of the increased power consumption inherent in moving to higher data rates. But we also know that this is a pace that's getting harder to sustain as memory transfer rates increase, especially as the underlying physics of DRAM cells have not changed quite a lot. As a result, looking at HBM4, some of the major memory manufacturers behind the spec are planning on making a substantial change to the HBM technology, starting with an even wider I/O bits going up to 2048-bit memory interface. The memory makers have also indicated that they are planning to stack 16 memory dies in one module, allowing for even higher capacity of HBM stacks. All of this is great news for AI applications that are hungry for higher capacity and increased bandwidth. Of course, it goes without saying that this also adds to the complexity of implementing an HBM system and will require close collaboration across IP vendors, DRAM manufacturers, packaging partners, and end customers. Let's take a deeper look at HBM4. With HBM4, there really is a fork in the road on how you implement these connections to the HBM stack that make memory access more seamless for advanced data centers and AI applications. I mentioned earlier that HBM4 is doubling the IOs to 2048 bits, essentially doubling the bandwidth from HBM3E for similar data rates. The HBM4 spec is largely backward compatible, except for some minor updates. One major change, however, is the memory base die is moving to a DRAM logic process, which is a FinFET logic process. This change will allow for integrating additional logic onto the memory base die directly. And this is a concept I want to explore a little more with all of you today. First, let's look at our standard JEDEC HBM implementation. So an HBM PHY and controller subsystem on the main die or the compute die directly translates your user commands into HBM command sequence, and the data is generally transferred through a 2.5D system, either a silicon interposer or an RDL type of interposer, or even a silicon bridge. Several such implementations are already in high volume manufacturing today, and it is a process that is fairly well understood. The next evolution to this, what we are seeing, is a custom HBM-based die implementation. This implementation leverages heterogeneous architecture where memory, I/O, compute are probably already disaggregated, and your die-to-die connections or die-to-die IP, they flank the shoreline for connectivity. We can then repurpose this existing die-to-die logic to now drive memory traffic. The UCIe subsystem with its smaller form factor and high bandwidth density provide a significant advantage over traditional HBM PHY subsystem. You can also reduce the valuable shoreline required for driving memory traffic and reuse these for other either compute to compute or compute to I/O connections. Lastly, I want to leave you with a little bit of a thought in terms of what else is possible is, you could also enable 3D stacking of the HBM directly on top of your compute die. This implementation would enable the highest throughput efficiency in terms of latency and bandwidth. However, the challenge remains, in terms of how do you deliver power and how do you manage the thermal gradient on the top and bottom die. And this will require some significant novel cooling techniques. But this gives you a sense of how HBM technology is evolving, and HBM4 is really at the crux of all of the innovation that is happening currently. Let's take a deeper look. Now that I've laid out all of the several implementation techniques with HBM4 generation, let's look at how you would potentially choose one implementation over another. First, let's talk about your standard JEDEC implementation. In this, you have a PHY and a controller subsystem on the main die or your compute die, which translates user requests into HBM command sequence, and this data is transferred over a 2.5D system and package configuration. You could either use a silicon interposer, which is largely well understood technology. You could also use redistribution layers. And for even higher data rates, currently foundries and OSATs are enabling higher number of metal stacks in the interposers to really drive those high-speed signals. Overall, the system performance is characterized by running your SI and PI simulations. So, you have three major components when you're trying to check for overall system performance. You have the PHY, you generate IBIS models for your PHY. You have the interposer, you extract the S parameter model for your interposer layout. And then you have the models for your memory. You ensure that your end-to-end data path is simulated to achieve maximum eye opening at the required bit error rate. This implementation leverages existing solutions and builds on learnings from previous generations like HBM2 and HBM3E. Another advantage of this implementation is it allows end users greater flexibility to choose the DRAM stack of your choice because it's essentially an off-the-shelf component. So you're DRAM vendor agnostic. And lastly, it's relatively cost-effective, and the cost model and the supply chain for manufacturing is well understood at this point. Next, let's take a look at custom HBM and how one would go about deciding whether this is the right choice for your overall system architecture. So creating a custom-based die using a die-to-die is a cutting-edge approach that involves tightly integrating your memory dies with compute dies to achieve extremely high bandwidth as well as low latency between the two components. In such an implementation, the memory controller directly interfaces with the HBM DRAM through a through-silicon via PHY on the memory base die. Commands from the host or compute are translated through a die-to-die interface using a streaming protocol or any other proprietary protocol. This allows for reuse of your die-to-die shoreline already occupied on the main die for either core-to-core or core-to-IO connections. Such an implementation requires close collaboration between IP vendors, the DRAM providers, as well as end customers to create this custom memory-based die. One of the advantages of using a custom base die implementation is that it enhances overall system performance by improving shoreline utilization on the compute die, which is more likely to be on an advanced process node. You can essentially pack more compute logic or implement other scale-out or scale-up connectivity IPs on the shoreline. Next, by tightly coupling the HBM controller and other supporting custom logic directly on the custom base die, you're eliminating the need for these commands and data to traverse through a package interposer. Low latency is particularly very important for AI inference decode stages. And lastly, your controller can be customized for specific workloads, configurations, which can again further go on to enhance your overall system performance. It's a very tightly coupled system, exactly giving the performance and workload requirements for your overall system. It's just optimized much better. Now that I've laid out, how one would go about choosing either a standard JDEC implementation or a custom, here is some more performance metrics in terms of data width, bandwidth density, and power that might further help inform your decision. So here's a side-by-side comparison. On the first column here with HBM JDEC, of course, HBM4 is going to 2048 bits. Assuming a data rate of 10 gigabits per second, we can achieve roughly about 2.6 terabits per second per millimeter. So this is normalized to the shoreline of an HBM5. So your bandwidth density is about 2.6 terabits per second. Your power is for per bit is about 0.36 picojoules per bit. Now, if you do a side-by-side comparison, and if you did a custom implementation with the 64 gigabits per second UCIe, which has 64TX and 64RX, you roughly achieve about 21.1 terabits per second, which is about 8 times greater in terms of bandwidth density compared to your standard JDEC system at a very comparable power profile, right? So, for per bit, it's about 0.35 picojoules per bit. And your reliability is also very comparable between the two systems. But what it really gives you, and I was explaining in the previous slides as well, it's really your maximizing your shoreline bandwidth density. And the jump in performance is massive when you look at bandwidth density. So having spoken about, all of the different components, one major component that has really come up is to implement such a custom HBM base die is your UCIe die-to-die connection. Here at AlphaWave Semi, we have developed a full UCIe subsystem solution for an open ecosystem. The UCIe is comprised of several components, including the UCIe physical layer, which features our electrical PHY that leverages silicon-proven analog IPs. It includes modules such as clocking, link training, sideband signals, as well as the logical PHY module with a multi-module PHY logic and a top-level floor plan that is flexible for all types of packaging options like we spoke about, either a silicon interposer, or organic interposer, or even RDL-type interposer. Additionally, we have a UCIe die-to-die adapter, which provides link state management, negotiates parameters crucial for chiplet interoperability, and manages reliable links through CRC and link-level retry implementations. The protocol layer maps either a PCIe or CXL protocol via a natively FLIT-aware mode and also provides a streaming protocol bridge for different types of SoC interfaces. Lastly, AlphaWave Semi offers a platform for electrical, physical form factor, and protocol compliance, along with a complete set of test vehicles for interoperability testing. One key element here, if you're really implementing a custom base die, is that the availability of UCIe on all of the leading foundry nodes across multiple technology nodes is critical. So here at AlphaWave Semi, this is our evolution of our UCIe IP, starting with our Gen 1, which is silicon proven, and it's showing you some of the eye-opening of our 16 channels of the 16 gigabits per second UCIe, which is our Gen 1. We have our Gen 2. You see the packaged module here running at 32 gigabits per second. And we've recently announced the availability of 64 gigabits per second, enabling up to 20 terabits per second per millimeter bandwidth density, which is essentially going to be used for all kinds of chiplet connectivity and interoperability. Next, we have thus far discussed all of the enablers, the technology merits of a custom HBM implementation, but you might still wonder, what does the supply chain look like for something that's so custom? Here, I've tried to lay out a very high-level engagement model of how this might go about. So first, I think we really need a three-way alignment with an end customer, the DRAM vendor, and AlphaWave, who are IP providers in this case, on the specifications of your custom base die. AlphaWave Semi can provide silicon-proven IPs like your HBM4 controller and your UCIe die-to-die IP, and can share a reference 2.5D channel model to analyze the overall system performance. Additionally, AlphaWave has also got the capability to build the base die with the HBM controller and UCIe, and also pack in any other custom logic that the customer requires. Once the base die has been assembled with the HBM DRAMs, we can go one step ahead and also build the full module to provide a KGD or a known good die for the custom base die that is fully tested and verified. The customer really has flexibility how to choose how they would like to work and engage with us. We provide several tiers of engagement models when it comes to implementing a custom base die. With that, I'll leave you with some key takeaways that I want to highlight as part of today's webinar. Deep learning and AI breakthroughs are made possible by advancements in hardware, and you can also say that their progress is also fundamentally limited by it today, which is why innovation in packaging technology is very critical to unlocking new paths for heterogeneous integration. And custom HBM stands right at the center of this innovation, driving the performance of next-generation XPUs and AI systems. This will require deep cross-industry collaboration to keep up with the pace of demands of AI. Thank you. And with that, I think we can move into some Q&A.
Perfect. Thank you so much, Archana. That was super interesting. And yes, we've had questions come in from the audience throughout, and still time if anyone has further questions, put them in the Q&A box to your right. So to kick off, first question that we have is, what kind of performance boost can be expected from custom HBM versus off-the-shelf HBM?
I kind of alluded to this earlier in my presentation. So in terms of, if you look at if you're really looking to maximize your shoreline density in terms of how much you can pack in your shoreline, because essentially today what we're seeing is that, because your single chip performance has completely maxed out, and the amount of shoreline that's available for communicating between chips, it's quite precious. So if you're really trying to maximize your shoreline density, your custom HBM provides a great alternative compared to your JEDEC implementation. It also comes with higher bandwidth requirements, and also you can repurpose already existing UCIe IPs on your shoreline to now drive memory traffic. You eliminate essentially requiring a completely new subsystem, but you're rather leveraging existing die-to-die solutions on your die.
Got it. That makes a lot of sense. So we've spoken about performance and enhancements. What about on the efficiency side? Are there any sort of specifics around efficiency that you can go into?
One thing is UCIe is a well-known technology at this point, right? So if you look at it from a system architecture perspective, if you are going into disaggregated systems, right, if your approach is not monolithic, there is already a possibility that you are disaggregating these systems either based on function. So, you have memory on a separate die, you have IO connections on a separate die, and you're packing all of your compute on your latest and greatest process technology nodes, right? So you've already disaggregated your systems. So you're essentially now in terms of efficiency, you are able to leverage and, place all of the memory on slightly older process nodes, specifically HBM, and reserve some of the, compute and logic on the latest and greatest process nodes. And so it brings about efficiency in terms of cost, right? So you are keeping all of your compute on the more expensive, latest and greatest process nodes, and your overall total cost of ownership, because you're leveraging some of the older technology nodes for memory and you're connecting them through a UCIe subsystem, helps you overall reduce your total cost of ownership, especially for large systems like XPUs and AI accelerators that we are seeing today.
Got it. And another question that's come in talking about sort of larger scaling systems, how scalable is custom HBM specifically for future AI models?
As with any new technology, I think there is some apprehension in terms of how well it will scale in the future. Like I mentioned, the JEDEC HBM system is a very well-known system today, right? It was the first chiplet of its kind. A lot of innovation went in with advanced packaging, to try and understand the overall 2.5D build. And I think it will be the same with the custom HBM implementation. I think the industry is carefully watching the progress of how custom HBM progresses. But I think we have all the pieces. For example, we have the IPs that are already silicon proven ready. We understand the channel in terms of 2.5D and even 3D stacking, honestly, how the performance looks like. So it's a matter of putting them all together and really understanding how power delivery, the thermal heat gradient across both of the dies. But I think all of the components are there for it to become successful. It just requires more collaboration, I think, across all of the different players, to see success in the custom-based die space.
Okay, great. Another question that's just come in is, today UCIe has separate TX and RX lines. Do you foresee implementations with bidirectional signaling over the same wires?
Good question. UCIe standard, if you look at the consortium, right, it was truly built for die-to-die connectivity. So in this implementation today, of course, I am presenting an option of how you could also drive memory traffic. And I know HBM subsystem is a bidirectional traffic. Not in the short term, because I think UCIe standard is still the cornerstone of, chiplet connectivity, right? We are kind of trying to utilize that for driving memory traffic. So unless we go down a custom route, which again, we don't want to customize too many components on your base die. We want to try and keep the option of interoperability still alive. So I don't see that happening in the near future, because I think if you look at why UCIe was originally developed, right, it was truly for driving traffic from one die to another. So I don't see that kind of mimicking HBM type of PHY type of traffic quite yet.
Okay, got it. And I think we've probably got time for one or two more questions. One that's just come in is, for AI designs, what are you hearing from customers about what is more important, throughput or bandwidth? And what is the best way to architect the design around these parameters?
Another great question. So the thing with AI is no one size fits all. It really depends if you're doing training, if you're doing inference. Even in inference, are you in an input stage? Are you in the decode stage? Each one of these different requirements in AI have completely different requirements in terms of network. So in terms of, if I just take an example of AI training, your network bandwidth is extremely important, and so is your memory density, right? You want to be able to feed the system as much inputs during the training stage. However, if you look at the inference stage, and particularly the decode stage, your bandwidth density is extremely important, and you also need extremely low latency, because your end user, you're kind of interacting the decode stage with the end user. You want extremely low latency in terms of the outputs, right? So it needs to parse through all of these billion parameters and provide a response. So it really depends which phase of AI we are talking about and what is it that your system is trying to implement. But overall, I would say there are, four cornerstones. There is network bandwidth. You have your latency to your memory, overall capacity, right? Also, you have systems where you need high capacity, HBM gives you the flexibility of high bandwidth, but capacity is limited in that sense. There are certain systems that need higher capacity, so an LPDDR or a DDR type of memory is more applicable. And then, of course, I spoke about latency as well. So latency, network bandwidth, your capacity, as well as your overall bandwidth efficiency in terms of throughput. So each stage of AI has its own requirements.
Got it. Okay, that was a really helpful explanation. Thank you. I think that's about all we've got time for on the questions today. But for any more questions that you do have, if we didn't get around to them, as I said, the AlphaWave Semi team will be in touch to follow up on any discussions. Thank you so much, Archana, for joining us today, and for everyone that tuned in. If you want to hear more from the AlphaWave Semi team, they will be at the AI Infra Summit in September, the 9th to the 11th, at the Santa Clara Convention Centre. We're really excited to have them partner with us once again this year. They will be presenting in our hardware and systems track. So more to come from them in September. Thank you so much again, Archana. It was great to speak with you today.
Yeah, thank you, everyone.